Hello, everyone. My name is John, and I'm with my colleague here, Barney.
Hi
This
everyone.
is so this is a podcast, a rough podcast, where we talk about computer graphics and papers in general. The idea actually come from um, when we met in a student seminar in Slovakia 2 months ago. So we were both basically authors, student authors, and we basically presented our papers on this conference. And during our conversations, actually, the idea came when we were talking outside in the place we were staying. We had to do an interview, and we found it so formal and kind of annoying. And we, as a young generation, we find it much more funny and interesting to do it in a more informal manner, which led us to this podcast idea. So yeah, basically, we normally plan to have more participants, which we met in this conference, Central European Seminar on Computer Graphics in Smolenice, Slovakia. But unfortunately, they are not with us today. Hopefully, but in the next sessions, we will have a more people around, so we can have a better, maybe more diverse perspective on things as well. So the idea is in this podcast that each session, each episode, we will have two different hosts, and each host will present a paper, not really present, but talk about a paper,
To be
and we
excited
hope,
about, like it's the
yeah,
job of the host to be excited about the given paper.
exactly. And the other members or the other participants need to also read the paper so that we can actually have a conversation ongoing. That might be sometimes difficult because all of us are actually students, but we will see. We will see. So yeah, and today's episode, Barney is the main host with a paper, and I'm the second host with my paper from the student seminar. And the idea is actually all of the participants will eventually also discuss their papers, which they presented in this student conference we had. But eventually, after we finish our papers, we mainly talk about the computer graphics papers that we find it really interesting. So it's basically this podcast can be seen as a reading group, but it's yeah, we will try to keep it kind of informal and try to have fun with it. So yeah, okay.
Yeah.
Do you want to
Oh,
say anything? Yeah.
yeah. We will certainly have fun. I have no fear of that. So of not having fun. So yeah. Also, we are throwing around some ideas for what we should call our little podcast or friendly reading group sessions. And actually, I
Right.
think we decided on CG papers and chill, where we
Right.
read CG
Thank you.
papers and chill. So that pretty much sums it up. So yeah. It
Exactly.
sounds fun to like expand on the background because as John was also mentioning, like one of the main ideas of why we thought this would be a fun idea is to maybe expand on the background and on the research on the parts of the research that doesn't really come up with like just
Right.
presenting at a conference, but like why you find it fun, how do you personally like this project, how did you happen upon this given project, and like yeah what's the
Exactly.
bigger picture of like of the person behind the research, and why did you get
Right.
excited about this specific research. So yeah and yeah, so thanks for the introduction, John. And also
Yeah.
as John also mentioned, like today we will have two papers. One of the papers, which I will talk about briefly and discuss with John, is actually a paper from Disney Research called Deep Scattering, which I will just share with you in a second. And then John will talk about his differentiable rendering paper, where he estimated some material parameters, which is a really fun project. So,
Thank
and
you.
with this, let me just share my screen.
Just a small note. We actually tried to did the first episode last week, but we are so good engineers in the sense we forgot to include the audio, so this is our second attempt. But yeah,
Yeah. So
let's
we
do
pretty much messed up the recording for the
it.
first time, and so we are
Right.
pretty much redoing the session. So yeah, we will
Right.
see. We will see. We didn't want it to go to waste. So yeah. We thought it would be nice to return to the
Right.
topics. So yeah, I will shortly introduce the paper. It's called Deep Scattering, Rendering Atmospheric Clouds with Radiance Predicting Neural Networks by researchers at Disney Research. I really like this paper. They essentially, what they essentially do is they teach a neural network to predict a part of the radiative transfer equation, where they estimate the indirect in scattered radiance with a neural network, and they achieve really nice results at almost like a fraction, not really a fraction, but like in much with much less computation needed. So faster but better results, essentially, or at least faster and comparable results. But before, so I highlighted some parts of this paper. But before I get into any of that, I think I will just really briefly go over the ideas in volumetric rendering. Right. I just recently had a lecture in it, so I just put up my slides here. Oh yeah, I didn't mention this, but yeah. I'm a student graduate student at the Budapest University of Technology and Economics in Hungary. And also I'm an incoming graduate student at Georgia Tech. So yeah, this comes with the introduction. And,
we have a American football team in Georgia Tech. Do you know maybe the short name? Go something.
Oh yes. Oh my God, yes. Go Jackets. Yes.
Go Jackets.
Yes, go Jackets. Okay. Yes. yes. So yes, exciting times. So yeah, back to volumetric rendering. So naturally, these are slides, so I'm just going to skip over some of the motivation and other things. I really like some scenes that I wanted to introduce. If you would like to read up more on volumetric rendering, I added a nice reference to production volume rendering, the 2017 SIGGRAPH course, which is a really nice resource if you would like to read up more on volumetric rendering. But yeah, this is let me just switch the views to continue scroll. Yeah, but with that, yeah, okay. So yeah, the volumetric rendering comes at a lot of areas. For example, in medical use cases, where you would like to show a user some kind of scan, for example, and you can do this with rendering slices with some alpha blending. But this won't really be the topic of our today's section, so I'm just going to briefly skip over them. And coming to ray tracing, essentially what you usually hear about in a ray tracing 101 course is you have a light source, you have some material at some surface, and you have your virtual camera or your eye, and then you would like to trace the incoming radiance or the incoming light rays that actually reach your eye or your camera. And so usually what you do is you have a light ray from your light source that bounces off of some surface and reaches your eye. But with volumetric rendering, you actually have some kind of volume, some particles in the way of the light, and when it enters, for example, a cloud or some cloud-like thing, then volume, then it somehow interacts. Then this volume, these particles making up this volume interact with your light rays, and some things can happen in this volume. So one such thing that can happen is that it will change naturally. So let us talk about a bit about the change of actually what happens in this volume, and more precisely, let us talk about what happens in a differential volume. So a really small amount of this volume, which we will call, this is just a notation, this nabla omega. This is essentially a notation for saying an infinitesimally small volume slice in the direction of the omega view direction. So this is our view direction omega. So we have a radiance at position x1 going in direction omega, and we also have some changed radiance after going through this differentiable volume section at x2 position, still looking at direction omega. We would like to see how it changed. So what was the change? So the radiance here minus how did we happen upon the change at position x2, and one of the things that can happen is we have some absorbing particles in our volume, and our photons can actually collide with these, or so we model our volume as some of these photons will collide with these material particles, and they will get absorbed. So we model this as a so there are so many material particles that we would like to model this volume as, or these material particles as a probability function, or we give a probability of how likely it is to hit one of these material particles and get absorbed. So we actually get absorbed with a sigma A probability, which gives us the probability of a collision happening while traversing this infinitesimal distance. Yes, so the way we can calculate how much radiance we have after going through this infinitesimal differential volume is we subtract the probability, we subtract the part of our initial radiance, or the part of our initial radiance that got lost, and we lost sigma A, or absorption coefficient portion of our radiance.
Right.
Yeah, so I'm trying to just be brief about it.
No, it's great.
Yeah, and then naturally not only absorption can happen, but we can lose some portion of our radiance due to absorption, but we can also lose some portion of our radiance due to outscattering, which means that we also hit a particle as a photon hits a particle, but it doesn't get absorbed, but instead it gets scattered in some direction, which we can then actually collect as inscattered radiance at another position if in our volume. So another thing that can happen is as we are interested in the radiance in a given direction, so in our direction omega. But then some photon came in from a different direction, hit a scattering particle there at that position, and it got scattered precisely in the direction that we care about. So we collect all of these incoming possible scattered photons, and we add these to our radiance, and then this means a net increase in radiance that we care about. And then we can also have an emitting particles, but we don't have them for clouds. Yeah.
Just a short question, because I kind of encountered the other day in a renderer, we most of the times define the amount of scattering that can happen, right? Like max depth of a scattering, because otherwise it would be too many scattering and it would be inefficient. Or am I maybe wrong?
Yeah. So essentially, so that's So what happens is you would like to trace a given photon, and then for example, you have an outscattering. So at this position, your photon scatters, but then it scatters again before it leaves your cloud or your volume. So you would actually like to truncate the number of these photon matter interactions, right. because if you don't truncate, so you don't say that, okay, I cut it off after 10 bounces, then it will be infeasible to actually track this. Right. But then what we will also discuss during the paper is that if you don't have enough bounces, especially with clouds which have high albedo, which means you have a high scattering, so it scatters a lot, then you have to gather these light paths with many bounces in order to get that really distinctive white color of your cloud, because naturally clouds are white because a lot of photons reach your eye from that given directions. But if you cut off some of the photons after, I don't know, 10 or 20 bounces, then those contributions of light won't reach your eye, so it will stay black. Yeah, we will see this when we go back to our paper, so we will come back to this. Yeah, and one last thing, as I mentioned, we can also have emitting particles, but we don't have those for clouds, and I actually haven't really seen a lot of emission component in real life rendering. So if you have some, I don't know, maybe so I haven't really seen a lot of applications for emittive materials in real life scenarios.
Right. And what was your colleague's name? Zoltan, I think. He had some example in his paper, right? Where he had some emissive participating medium.
Yeah. He did. So it comes up.
Right.
Yeah. That's right.
Mostly in
I never
renders.
distinctly remember render with that. But naturally, I don't know if you have some radioactive material, then it
Right.
can give a nice glow.
Right.
But even if you have some fire, for example, like it's not necessarily the smoke that gives off the emission, but instead like some like you have some lamp or some light source underneath your smoke. So I'm not 100% sure about different ways to do this. So it might totally be that, yeah, you just add some emissive part. But yeah, anyway, for rendering clouds, we won't have an emission term in our equation. And actually, I don't know if I mentioned it, but I think I haven't. This inscattered term will be the one that we will try to approximate to the neural network in our paper that we will discuss soon. Right. So essentially, this is a really hard problem because you have to integrate all of the contributions from all of the directions, from which directions we could potentially have incoming photons, and then this becomes this becomes really computationally difficult because then you also have to calculate the same component to derive how much light you get from there. So it essentially becomes a recursive problem, right. which is really difficult. So big, and also because of the bounces, essentially. So you have to suffer a lot of bounces. Yeah. So I think I've been staying with this slide for too long. So yeah, the main thing is that we naturally we will have to integrate these infinitesimal changes in radiance over longer distances that we care about. So we would like to sum up the losses and then sum up the gains of radiance. And this is one distinctive thing that we will come back to. We can have homogeneous or heterogeneous materials, and for homogeneous materials, the density or the probability that we hit a material particle, which is essentially the same thing, is not dependent on the position that we have, but the heterogeneous material is dependent. Like the density of a heterogeneous particle is dependent on the position that we are at. And naturally, if this term depends on the position, then it's more difficult to solve it. Yeah. So and then we also have an inscattered radiance, which I mentioned. So we naturally just integrate over this S square is a notation for the sphere around our position. So all possible incoming directions omega dash. Yeah, and we also have the phase function, which is kind of like the BSDF in surface rendering, which tells you what's the probability of a light coming from direction omega and then scattering into direction omega square, omega dash at position x, and then this has to integrate into one because this has to be a probability function. So we don't want to lose radiance or gain radiance because of this phase function. And we usually also model this, and our paper at hand we also model this as an angle between the incoming and outgoing radiances, because usually it's not dependent on it's dependent only on the angle of our incoming and outgoing radiances. So it has a symmetry. And then in the easiest case, we can have an isotropic medium, which is 1/4 pi, which the phase function of which is 1/4 pi, because it's an even, so it's evenly distributed among all possible directions. And otherwise, we call our material anisotropic. Yeah. And here are some examples which are actually from the paper, which we will discuss in a couple of minutes. Because I really like this. I really liked this illustration. This is an illustration of different phase functions that usually come up with rendering volumetric. So we have our isotropic phase function, which is 1/4 pi. So this is just a constant function over the possible directions. And then we also have a Henyey-Greenstein phase function which has a parameter g, which can so if you just this can range between, I think, -1 and 1 or so, and if you choose it to be 0, then it's just an isotropic phase function. But then, for example, if you choose it to be g equals 0.87857, then it becomes a forward scattering phase function, so it scatters more forward.
Right.
And then we also have a Lorentz mean. It's a really intricate phase function. And then we have the chopped variance of the Lorentz mean phase function, which we will discuss during our paper, because they actually ended up using the Lorentz mean and chopped Lorentz mean phase functions. More precisely, I think they ended up using the Lorentz mean for the first scattering, and then the chopped Lorentz mean for the scatters after the first scatter. And yeah, but we will come back to this. And yes, I will skip over these parts. And yes, we would like to assemble all these parts and then sum up these contributions from all of these effects happening simultaneously. And this gives us our radiative transfer equation. And this is literally the same as what they give in the paper, with one single exception, that they don't use sigma for the exclusion coefficient, sigma s for the scattering coefficient, but they use mu t, mu s, and mu a. No, sorry, they don't have the emission term, but they use mu for the different probabilities. So that's the only difference. And I've seen people use sigma and mu
interchangeable. Oh, okay.
So it's interchangeable between papers, but they usually just stick with one for, and naturally they are
right.
So they are yes, choose one. So yes, so our problem is to estimate the change in radiance L traveling along direction omega through a differentiable volume element at point x. But this is telling us what happens to the radiance in a forward fashion. But we would naturally, if we would like to integrate, so sum up all of these small changes, then we have to integrate this equation. So let's integrate it. And yes, here I really like. So I really like to substitute stuff to make it easier, maybe mathematically. So I like to give it a more familiar notion of like I changed this nabla omega to a dx to make it more familiar for our purposes. And I also changed here the Lx omega to be only a function of x, so it becomes easier to like maybe tackle it mathematically with what I know about. So here this kind of gets. So I'm not sure about the proper way to write it. I've seen people write it in multiple ways, because this is a distance, but it's also a vector. So it's and if you have this differential operator, then it's telling you that. So and anyway, I like to just think about this as a distance here for our purposes, and I think it just becomes easier to maybe just to toss around the different parts mathematically. But yeah, so to keep it short, we have an exponential extinction where our radiance function is dependent on the radiance function itself at each position. So this is what we call an exponential extinction, where a portion of our function is lost at each time step. So if we integrate this, then we will just have 1 over L and sigma t on the right side. And we would like to integrate this, and naturally the integral of this, just using our usual calculus knowledge, the Newton-Leibniz rule. We have these logarithms, and then if we raise both sides so we take the exponential of each side, then we arrive at an exponential extinction. But yeah, maybe this is unnecessary to understand it. But what we should know about is that we have to solve this integral essentially to find how our radiance changes as it travels for distance s. And this is the way I try to understand it, and maybe like.
Oh, it makes sense. It makes sense. Yeah.
And then we would like to solve this integral, which is sometimes also, so this exponential term is also sometimes written as the transmittance coefficient, or usually it's simplified to just a function t and between positions x and y. And this tells us how much light gets lost essentially. And then this exponent is called the optical thickness of the material, which is also sometimes just called tau, between x and y. And yes, and then our transmittance becomes the exponential minus tau.
Right.
Yeah. Over distance d. So sometimes they don't write it as between x and y, but over distance d. So this is essentially the same thing. And then we would like to solve this integral to give us our net reduction factor. But in order to, so this is really easy to solve, is if this is a constant function naturally. So this is just a constant function, and it's really easy to solve. But then if it's some crazy function, or maybe some measurement of cloud density at multiple positions, then it becomes unfeasible to solve it properly. And then just going back, so we wanted to integrate this radiative transfer equation, and then what we end up with is this radiative transfer equation, but the integral version where and this is almost so this is the prelude to our paper. So after just briefly showing you this, I will go over the paper. So what this tells us is a radiance at position x looking in direction omega is given as an integral. So we would like to integrate all the way from our current position to infinity. And the way we can get radiance is from in-scattering and also from emission if our material is emissive. But then we lose, but we lose that only the transmittance portion of these gains actually reach our eyes. So we would like to integrate this. So at each position, only the transmittance portion of it, only the reaches our eye, and we would like to integrate this. But then we actually cut off this integral at the closest boundary surface z. So for example, for the purposes of rendering clouds in our paper, this will be the boundary of our cloud, because outside of the cloud we don't have any material, so we don't have these mediums actually interacting with our photons. So we like to solve this integral until the surface of our cloud, or the closest surface, for example. And then we also have a term. So we would like to solve the before mentioned integral inside the cloud, but then we also have a term that gives us some radiance at this closest surface point or boundary position, but only the transmittance portion of this reaches our eye, where our transmittance is between our current position x and the surface position z. So how much do we actually receive from this radiance? And then this could be like any kind of shading that we know about. So this could be just any kind of shading, like a Phong shading or whatever at the surface, or just some light coming in, sort of sun outside our cloud, for example.
Right.
And then we have tracking, but I think we should hop on over to our paper.
Sure.
And then when we happen upon this, I think I will mention data tracking maybe briefly if it comes up, because it's a really nice way to solve.
Great slides, by the way. I mean, I think they're really great, to be honest, because sometimes it's really difficult to explain these mathematical ideas if you never have get familiar with them previously, but they kind of build up, so you get the ideas in a procedural way, in a good like understandable way, because sometimes it's really difficult. You get the whole equation at once, and it's just you have to think about it, but the lecture continues and it's difficult, but this kind of builds up. So yeah.
Yeah, thanks. Yeah, I also really like talking about it because I think it's just so fun because it's like it's a really difficult problem, you know, like rendering clouds and stuff.
Right.
But then you have these components that you can build
Right.
up really nicely. So I also really like reading about reading like the SIGGRAPH volumetric rendering course
Right.
slides, and because I think it builds up really nicely, and then you can take each component and really think about it, and I think it's really nice to grasp. And yeah, that's also, I think
They're
that's one of the
really
reasons I like
intuitive.
computer graphics
Yeah.
in general, you know, like
Exactly. Yeah.
yeah,
They're really intuitive. Like when you think about the equation, it makes sense. Like you get the idea, and also in your equations that you showed, it makes sense. The transmittance parts and the terms of the equation are intuitive to understand. Yeah.
yeah. But one note about the slides that like I will never ever uh, try to create my slides in LaTeX again because
Oh,
actually
okay.
I made these slides using LaTeX, but it was such a headache at some point. So, but it was a lot of fun, and I really like how they turned out. But it's such a hassle to do slides with LaTeX. Also, it's really messy to get like animations in. So we'd like to have
Right.
some animation or anything, and yeah, it's just yeah.
That's
So
why professors never change slides, I guess, because I
yeah,
remember from my bachelor time, like probably slides were prepared 20 years ago, and you just see the formatting errors, and it's just disgusting to look at.
yeah, yeah, maybe, yeah, yeah. But also, I think I haven't seen a lot of professors do LaTeX slides, so but I
Right.
can understand
Mm.
why. But yes,
Mm.
some yeah, 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 yeah. So yeah, let's hop on over to our
Okay.
paper. Yeah, so it's called Deep Scattering Rendering Atmospheric Clouds with Radiance Predicting Neural Networks, and it comes from Disney Research and ETH Zurich. And as I mentioned, I highlighted some parts that I found interesting, but I don't want to drag on all the way. So John, if you find anything particularly interesting, just hop on,
Sure.
and yeah, just feel
Will
free
do.
to,
Yeah. Uh, Just a short thing. I think this is one of those papers are fun to read. Like there are some papers it's such a hassle to read, but this one was so fun and easy to understand. It's so I would definitely recommend to everyone also to give it a try and read the whole paper as well.
yeah.
Yeah.
Yeah, 100% agree. Yeah, I also really agree. And I will come back to this, but I also really like the way they introduce neural networks to our problem. So this will come. So I also really liked reading this paper. So that's why I thought we should get this
Yeah.
as one of our papers for reading circle, because yeah, I think it's really nice to understand all the problems, and also the way that they talk about neural networks is that they are universal function approximators, and they literally tell you what they approximate and how they approximate it, and I think it's just really a fresh air to be like kind of sober about what AI or deep learning or neural networks are. And yeah, anyway, it's just my little notion of why it's really nice to read about neural networks just being function approximators, which they are. And I think it really
Right.
shines through in this paper. And it's not really the purpose of the paper, so it's not really a purpose to, so it's not really just neural network, but it's really nice to yeah, just to get like a really concrete problem. And yeah, anyway, let's head into the paper. So yeah, so what they do is they use a neural network to pre-learn the spatial and directional distribution of radiant flux from tens of cloud exemplars. And so why this is difficult? In the introduction, that in the introduction they mentioned this, but I also hinted at this, that that clouds are that the visual appearance of clouds is dominated by multiple scattering of light, which is often on the orders of thousands of photon matter interactions. And yes, this is a difficult problem. And oh, sorry, I should have went with the continuous scroll here too. Yes, so and then they introduce related work that other people have been using to solve this problem. And just to show you the figure of what it actually means to cut off these photomatter interactions at some particular position.
Mm-hmm.
So here, for example, they used only one bounce. essentially to render this cloud. And it also shows that it took them only 0.017 hour to do this. But yeah, the cloud was black because naturally you didn't get many of the photon contributions that actually would have reached your eye, but they cut them off. Then you have 4 interactions, 16 interactions, 64 interactions, and then all interactions. And you can also see that this just goes up and up and up to 34 hours for rendering all interactions. So that's just crazy. And yes, so they wanted to speed up this recursive problem, and this is the problem that they trained the neural network for. And we will come back to this in a second. So they also mentioned that this is nice for throughput-oriented applications, they use deep neural networks, and one of the problems is how do you actually input your scene into your neural network? So you actually have to decode your scene, into your neural network. And I don't want to hop too much over the place, but I will just free flow and then So you actually would like to somehow code your scene and then feed this into your function, which is in this case is a neural network, and then actually try to get some ground truth, because naturally you would like to compare how well your neural network did given this problem that you have at hand. So the way they actually decode their scene is they have a descriptor of their cloud geometry, which is a multi-level stencil. So what they do is they go more into its details, but they use k equals 10 levels of this hierarchical scene descriptor, where they have a local frame centered at x, and then a z-axis towards the light source, which is shown here. So you have your view direction, and then you have your light direction, and they orient these stencils in the direction of their light source. And then they have 10 levels of this, so only 2 of them are highlighted here. And then they essentially sample the cloud density in this hierarchical manner. And then what they also show is that so they achieved much better results when they didn't feed all of these layers in all at once, but instead they fed them in hierarchically, so only 1 level at a time. But before showing you this, I will just briefly go back to what they actually would like to approximate. So as I already showed you in the slides, this is the radiative transfer equation that I also had on my slides, with the only difference that the coefficients are called mu, and I call them sigma, but it's the same thing. So you have the integral version of this, where you cut it off at a boundary b, which is on a hypothetical boundary omega that encloses the cloud. So this is essentially the border of your cloud. You cut off your volume integral there, and then you have a term which is the transmittance, so how much of the light actually reaches your eye, and the radiance at the boundary, which is essentially your, as far as I understood it, it's essentially the sun or your light coming from the outside.
Right.
And then you also have your integral. So you have the inscattered term here, which for all positions in the integral tries to calculate the inscattered gradients from all directions sigma squared, where they have this d omega hat for all incoming directions. And actually, this is the equation that they approximate with their neural networks. But this is not precisely the thing that they approximate, but instead they factor out the direct inscattered gradients. So they actually only approximate the multi-scattered transport, which they also call the indirect inscattered gradients, which is the scattered gradients that reached disposition after at least one bounce. So they actually factor out the photons that reached this position without bouncing before. So if this is the first bounce of the photon, they don't take that into account. So they call this direct in-scattered radiance, LD, and they factor this out from this integral.
Just to reiterate, so they basically approximate the indirect in-scattered radiance, and the direct scattered radiance with the other terms that we saw in the previous equation are calculated to normal rendering scheme, right? Okay.
Yeah. So what they do, and this is also really nice, I think, to like see how you can just cherry pick something to approximate this neural network. So you have your usual methods, Monte Carlo simulation or Monte Carlo
rendering,
solving or integral estimation, and then at the point in your code, so you code all of this up, and at the point in your code when it reaches like get indirect in-scattered radiance, then what that calls is just a neural network. It's a function, but internally it's described as a neural network, but that's essentially just matrix vector multiplications and some ReLUs and like skip connections or whatever. But actually, I believe that the neural network itself is easier to code up. So I think it's much easier to describe mathematically than, for example, Monte Carlo simulation. So it's like naturally you can go crazy with neural networks, and they do in recent works. But actually, like just your good old MLPs that they also use here, it's quite straightforward to code up. So it's just vector matrix multiplications with like ReLUs. There's cut off the negative part. And it's actually quite easy, and then you have like a skip connection, which
we discussed this last failed attempt on our podcast, and I kind of find it initially difficult how actually they can integrate that solution into the underlying Monte Carlo rendering. But with your explanation, you just basically encapsulate a part of the equation, and for that encapsulation you just use your approximation using your ML approach, and you then bring them together and just combine them and metric multiplication. Then that's pretty much it, actually.
So just reiterating just one more on this. What I also really like is that like in other works, you can just cherry pick another function. So for example, approximating some external force component in a physical simulation. So you just have your good old physical simulation, spring system, whatever, and then you have a plus external force component acting on each particle at each grid cell, whatever. And then you just approximate that as a neural network, given your model, given your state of your system. So I think that's really powerful. And I also really like to think about neural networks as universal functional approximators, because they are that essentially. And also Monte Carlo estimation is also just like a way to solve some equation that you have. So in this sense, they are so there's the same thing. So Monte Carlo is not the way clouds work. Monte Carlo estimation is just a way to solve your integral by using your estimation. So just by sampling and
sampling.
So I really like to draw the line between your model and the way you kind of. But then you can also use neural networks for finding your model based on data, which is really cool, I think. But I'm getting way ahead of myself. So to go back to our problem, because I kind of went all over the place. So to go back, so for neural networks, you would like to approximate a function, which they here call G, which takes in your description of your scene, Z. And you also have some theta. The difference between these is that you optimize for theta usually. So you take the gradient of your loss function with respect to omega, and then you do some gradient-based optimization scheme to find the best possible theta. So to solve this argmin problem for theta, to find some theta hat optimal theta parameters. And then naturally, this has to be some errad D to R problem. So you would like to, so this means that you have to translate your scene and your geometry of your cloud and everything into a row or column vector of numbers. So like essentially like a column. So essentially, yeah, some scalar errad D vector. And then you map this vector into one real value, which will be your indirect in-scattered radiance in our case. So that's just one single value. So you would like to find the best possible theta parameters given your z values.
Right.
Or rather, the theta that works best for all possible values of z given your loss function. And yes, I think I just skipped over. No, they didn't introduce it yet. So yeah, we will go back. But the loss function is essentially just your good old. I think they just use a
mean squared error.
A mean squared error, yeah.
Just logarithms, if I'm not.
Yeah.
Not really sure. Yeah.
Yeah. So here they show it's just yes, squared error loss function. So that's just the mean squared error. Yeah. So and then they But more generally, you have a loss function L. But in the easiest case, usually it's a mean squared error.
And then it quantifies the quality of that current solution during that iteration, I guess.
Yes,
right?
yes. So that's the objective of your loss function, to actually say how well your neural network did. And in order to form, like for your loss function, you would like to have your function G, which is your neural network, and then you would also like to have a ground truth data. And so you would like to compare it with something for our intents and purpose, for our current intents and purposes, which is actually some pre-computed data. So they pre-compute using many bounces and Monte Carlo simulation and ray tracing. So some really good looking clouds using a lot of resources, a lot of time, lot of energy. But then these stay constant and they just try to find the best thetas that come as close as possible to these ground truths. Yes, and then we didn't discuss what actually is this Z. So we were discussing this multi-hierarchical, so this hierarchical stencil here. But this, they call this our shading configuration, which they denote S. So they would like to describe the light source and the density structure of the entire cloud with one single vector of numbers. And they call this setup S, and they call it a shading configuration. And then they find a descriptor P or phi that translates this shading configuration into this row of numbers or column of numbers Z to represent S. So represent our scene, our current shading configuration. Yes, and then they have a lot of label data, which is essentially just a lot of pre-computed clouds or pre-computed radiance values, and they have n samples, where they have, okay, what was our shading configuration here, and what did we calculate at that position looking in that direction, and then they have n number of these pre-computed ground truth training data. Yeah, and actually with this we come to our actual deep learning solution. So the way I also like the way they describe their layers. So they have 10 or k levels, but k then will equal 10 levels of hierarchical stencil. Sigma, and then they have a block for each of these. So it's just so this is one block. This is one block K for one level of the stencil, and then for each of these blocks, they have oh yes, an angle gamma. So they don't formulate it as yes. So as I mentioned, you can formulate your, like, not with omega and omega dash, but with the angle between them. So I think, if I'm not mistaken, gamma here is the angle between the incoming and outgoing directions, I believe. And then what you have is a layer is a block K for each of these layers. And then what comes in is the output of the previous layer. And then for each level, you feed in progressively your description of your shading configuration, or the description of your scene. So you feed in for each block only one new layer of this hierarchical descriptor. And then you just have your usual MLP, so a matrix vector multiplication. So this VZ multiplication is for the new fed-in layer, and then you also have another set of weights, so another set of W set of weights, or set of weight in this W matrix that you multiply with the incoming, so the output of the previous block, and then you also have a bias that you usually have. And then for their non-linearity, they just use a good old ReLU. And then they have one new layer, and they just have one, they just combined the set of weights into one matrix W here. And then you also have another bias. And then you have a skip connection that they usually have from the output of the previous layer to be combined with the output of the current layer. And then they also have a ReLU activation before feeding their output into the next layer. And then after K, where K equals 10 in their solution, number of these blocks, then they have three more layers, but these layers are essentially the same, but they don't have a new layer fed in, but these are just three new MLP layers, so just three new set of matrices, weight matrices being multiplied with their input plus some bias using ReLU. And then after these 13 layers, so K plus 3 layers, they have their output, which should be the indirect incoming radiance.
Right.
Yeah, and
this,
yes,
this figure is such a good figure, by the way. I think they made it understandable, the whole process and the layers with these themselves.
Yeah, I think it's quite nice once you wrap your head around it, and also I think what is also really nice is the description they have here. So I really like how they formulated, like with these sets of weights. So here they write that you have your F1, which you have a new layer from your descriptor, but then you have for the last 3 layers, you have only your incoming F1K values. So I think it's quite nice. And then as I mentioned, like the numerical entries in these matrices, VW and these biases will be your trainable weight, and they collect them in theta. I believe. So these will, so here they write it pretty nicely explicitly that theta is the set of all of these trainable parameters. Where you have V's, W1s, WKs, W2s, and B1s, B2 up to from K equals 1 to big K, so 10 of these, but then you have your last M layers where K will be 10 and M will be 3 in their proposed solution. And here they describe the training procedure. I'm just skipping over rendering. We can go back to that if we would like to. The training is like a good old ground truth based setup. So you have some ground truth, and you have your loss, which in this case is a squared error loss. You take the mean of these losses as described here. So you take the mean of these losses, where your loss is your mean square. So yes, so here you see the
logs.
Yeah, and they also have these logs here. And they also have like these logs and yeah. Actually, I don't remember. I didn't hear them discuss why they added these logs, but I think it makes sense.
Okay, I was thinking about that because I guess they have some low values they want to push them up. Is that the reason?
I'm pretty sure it's for making it numerically more stable, but I don't remember them discussing it actually. Do you remember them discussing it?
I also don't.
I think
because I found it really interesting because in my paper we also used in some kind of a similar approach where we have an objective function, and I was kind of interested which objective function they were using, and I suddenly saw this log terms, but they don't really talk about it. But
I am pretty sure it's kind of like a scaling of numerical values, because essentially both of these are scalar values, and naturally you would like to get nice scalar values to make training feasible, because then you take the gradient of this. So I believe this is essentially just like some transformation of these scalar values, and then they have this 1 plus the actual output, and taking the logarithm of this. So I'm pretty sure this is just like a transform of but I don't remember them discussing it actually. But,
yeah, me too.
Maybe they felt it's like trivial.
Yeah, could be.
Yeah, but yeah, let me just find log, because maybe I'm just methodologies, technology, and analogously, and then they have logs here, logarithm.
Logarithm.
They just write here between the logarithm of the network output and the I don't think they discussed it anymore. And then they had a meteorology. Okay. All right. So,
probably, as you said, it's something quite
it's just a transform of
common, probably.
So and then they split the training data 75 to 25 between non-overlapping training and validation subsets. So I actually found it a bit high. So I found it interesting that, I mean, 75 and 25 sounds like 75 sounds like relatively low and 25 a bit high to me, but I'm sure they had the reasons, so they didn't elaborate on this. Maybe they just had so much data on their hand because they could just simulate whatever many clouds or whatever many radiances. And naturally they use the training for training, and then the other one for monitoring convergence and selecting the hyperparameters, which you would like to do only once. So you would actually like to run your proposed values, optimized values on the evaluation ones only ones. But actually here they say that they didn't use like here they use this for tweaking the hyperparameters, but usually you would like to have like what I just mentioned, but I realized that I wasn't referring to the validation section that they used here, but instead they don't say that they have a test set here. And then at the end, they actually show some convergence graphs here. So convergence of validation error. So here they actually don't have a test. So usually you would have like a test. I'm not sure about how this would work ideally, but usually I see people use validation for training, and then you have a test set. But maybe that's more crucial for doing like real life problems. So you would, because actually if you use your training data, be it validation or whatever, to actually tweak how your system is doing, then you actually miss out on being able to see how well your network is actually doing. So for example, if this is some real life problem, so for example, I don't know, self-driving cars or something like that, you're actually not allowed to use the knowledge of how well your network is doing on a given number of training samples to actually tweak your network, because then you actually can't see whether your network will actually do well if it's deployed. So actually, I remember people discussing this, and I'm not 100% sure about how it works. So maybe it's completely all right for their purposes. But
that's interesting point. Yeah. I will also remember in the paper.
At least this is something that like professors usually really try to get into your head when you take a deep learning 101 course, that you would like to have some totally distinct set of data. But here they have a 75-25 training validation sets for tweaking the hyperparameters. Oh, and by the way, if you would now that I think about it, so this actually shows you how well your solution generalizes. So maybe if you don't want your solution to generalize too well, but you would like them to be as good as possible to the examples you have. So if, for example, you have a given number of cloud setups, so you have like only that many cloud setups, I guess, or where you have your light position at whatever position, and then you have your cloud with some cloud-like shape, then maybe it's not that important to anyway, I'm just brainstorming here. So
possible, yeah, makes sense actually. Yeah.
So it's not like you will go into the real world and, I don't know, do stuff.
Right, it's right, yeah.
Maybe
not dangerous to the external people.
Yeah. And also by the way, at the end they show that it doesn't generalize that well so you actually have this cloud-like formations here, where you have nothing cloud-like, because your neural network is actually trained on cloud-like stuff. So here's the path trace reference, but here they had the neural network approach. I would actually like to toss the ball to you, because I think we are kind of running out of time, and I would actually like to ask you, which part would you like to discuss about this paper? Because I feel like I've been just free soloing, but which part would be?
No, I think it's in general. Maybe the results section would be interesting. How their approach then eventually performs, and how I think the visuals are also really.
Let's go over the results, and then will we also have time to like talk about your research and your paper?
We can also briefly talk about it. Yeah.
Cool, because I think there are some really interesting connections to this paper, like on a I don't know, on a philosophical level maybe, and also on a concrete level. Yeah.
Basically, it's also optimization in that sense. Yeah, you try to estimate something.
Yeah, and we were also just hinting at it earlier. But what I really like to think is that like you use differentiable rendering, and here they didn't use differentiable rendering. So the rendering part, they didn't make it differentiable, but then they kind of injected into their rendering some differentiable subcomponents. So they, in the end, you kind of have differentiable rendering, because you have some. So they kind of introduced like a new set of parameters, theta. And then they formulate, like they have this shading configuration descriptor, but that's what you have there. But then you also introduce these theta parameters that make your problem differentiable. So I kind of really like to think about this kind of difference between differentiable rendering, where you have your whole rendering problem differentiable, and here you kind of integrate a differentiable subcomponent into your rendering, and then you formulate it in a way that you can take the gradient with respect to something that you care about. Right. So I think it will be like an easy.
I will also hint some points, and because last time I kind of missed some points, and this time I kind of look at my old notes and saw something that would be interesting. Also briefly mentioned, then I show some of my stuff. Yeah.
Oh, that's cool. Looking forward to it. Okay, sounds great. Yeah, okay, yeah. So with that little hint on what's coming up, So let's jump back to our results. So yeah, that's right. Because I actually didn't even say you how well, or like we didn't discuss how well they actually ended up doing. Yeah. So for the implementation, they used TensorFlow, which is a little fun fact. And then they naturally had some nice NVIDIA GPUs on their hand, and at the time, the NVIDIA Titan X Pascal GPUs, and we were also briefly mentioning this the last time we talked. So they actually used CPUs for creating the path trace reference images, and they used two Intel Xeon E5 something CPUs, and I think it's quite interesting, because they say they also experimented with GPU path tracing, but however, they had like 2 times slower.
That's really interesting, right? Like
yeah.
we also talked about it last time, and it's just interesting because we eventually decided or thought about it and said probably the memory consumption influences the effect, the efficiency of the GPU.
Yeah, it's
rendering.
quite interesting. Yeah, I think that's what they're hinting here at, because they say that the GPU's path tracing was close to 2 times slower than the dual CPU setup due to the incoherent memory access inherent to tracing long light paths through clouds. I think it's really interesting because that's what they are getting at. So you have like these long bouncings of photons. And then so we actually end up having to access density data at really different point in your kind of memory or in your cloud, and actually it really becomes a bottleneck. And I think it's also really interesting because it's like also like transferring data between the CPU and GPU is also really a bottleneck nowadays. So that's really interesting. It's interesting to see. And I also would just like to pull up. If we are just talking about this, I would like to just plug in that I also read a technical report about rasterizing volumes and surfaces for crowds on Sol. So this is a really short technical report from Pixar, Pixar research, where I was really blown away. I mean, I might have.
I remember this one.
Seeing it written down, it's really interesting. Yeah, so they actually say that when they were rendering the Sol world, they estimated the scene to be around 100 terabytes for an average of 2 hero characters per shot. And then they say that the projection actually exceeded the actual peak usage, so it was just 80 terabytes of data. But it's still crazy. So it's still crazy. So that's the dimension of the numbers we're talking about. That's the
and I'm struggling with my 6 gigabyte VRAM on my computer, so they're talking about 80 terabyte of memory consumption.
Yeah, that's just crazy. And just imagine like having to optimize your IO for actually accessing this data, and then you also have to simulate this data, because like it keeps moving, and especially for Sol. So have you seen it, by the way?
No, I haven't yet, but it's on my agenda. I will.
Really? It's really nice. I think it's one of the most beautiful movies. Yeah, I could say this for any Pixar movie, but I think it's really thoughtful and heartwarming. Yeah,
I remember watching the other one with the feeling. That was also great. I'm not really sure whether it was Pixar, but I think it was Pixar.
Which one?
With feelings and then they.
Of course, Inside Out. You are
Inside Out.
That was Pixar. Yeah. Oh my God. Yeah.
That's also great.
I think that's hands down my favorite movie. Like if I would have to name the favorite movie that I have. Okay, I would have some difficulties with that, but I think something that would come to the top of my mind would be Inside Out. I just absolutely love that movie. That's so nice.
I heard that they are planning to have a television series for that.
Really?
Really?
Yeah.
Really? I mean, if I read it correctly, but I kind of.
Oh, that's cool. That sounds cool.
Yeah.
Oh wow, that's really cool. Yeah, but for Sol, so certainly with the Sol. So what they had is they kind of had this ethereal other world, this kind of like heaven-like setting, where you had souls, and essentially where this space was actually made up of entirely volumetric. So not entirely, but like mostly volumetric thing, as you can also see here. So each character was actually like a volume blob, essentially, or like some volume, and then also your setting was like, so it's kind of like an edge case, so to say, in this sense. So it's but still, yeah. even for clouds. And naturally, the bigger resolution you have, the more difficult this problem becomes.
Right.
So here they had like 1280 by 720 resolution for the rendering, at least. So, but I think they also mentioned somewhere the dimensionality of their cloud data. Do you remember that?
Dimension of the cloud data.
I think the link that they provided was dead. I believe.
Ah, right. Yeah. Last time we couldn't find the
here.
page.
So a subset is available here, but if I go into Safari and open it, so it says it's missing. So it says it's missing. So it's missing authentication token. So what I remember looking at this release or kind of this research site here, and you had the publication PDF, and you had like a nice YouTube video of it, and you had an abstract. So, wow. Oh my God.
Okay. I also missed it.
Maybe they have two. Maybe they have two sites. Wow, that's really interesting. Because I distinctly remember it not being there the last time I checked.
Yeah, I mean, we looked it up together. Yeah.
Right?
Maybe. Yeah, we looked it up together. We probably missed it. Maybe it was on the bottom of the page. Maybe that's why.
Yeah. In fact, I think I scrolled down. I'm not sure.
Yeah.
That's it. Anyway. So I think like they have all of their volumetric data here. Yeah, because it's really strange, because I actually remember finding it like the first time I read it like a couple months ago. But then when I tried looking it up with you, we didn't find it. Anyway.
Yeah.
Anyway, so yeah, but I don't remember. Yeah. So these are artist created clouds, and the subset is available. For everyone looking, so yeah, let's go and find it. But I actually don't remember them saying how much it was in terms of gigabytes. Fogbo. Okay, maybe I will give up on trying to terabytes. Yeah, I don't remember. But anyway, it must be some huge number for these volumetric data sets. Yeah. Anyway, so yeah, circling back. So they trained these. So they actually ray traced these clouds to get their ground truth using a dual CPU setup. Then they ran the training, and their training ran. I also think I highlight So it took only 12 hours of training on a single GPU, which I think is actually mind-blowing, because I think this is just so strange if you think about it. Like it's better. It's actually faster to train a neural network than predict it, than predict or render using your neural network, than to actually use this dual CPU setup to actually render your clouds using. Like it's crazy. Like it's actually faster to train your neural network and then render your clouds. It's crazy.
Am I correct when I say like it? Let's say, so in this case, Disney trained the model and publishes it, and as a third-party user, you can actually directly use their trained approach and trained model, and actually then integrate it in your rendering system so that you can basically use their approach. So basically, you don't, as a user, as a third-party user, maybe you don't really have to train anything. You just download.
Sure. Yeah. So I think the generalization is like one problem probably. So I think that could be a problem. But I believe that they actually say that it's temporally stable. And they also say that it's like also for retraining and adaptation. So I think the initial training takes 12 hours, and then tailoring their performance to a particular kind of cloud or specific cloud formation is thus relatively easy. So like lightweight retraining could also be achieved by employing the idea of progressive networks. So I think there are So it's kind of funny, like, they also say this for ChatGPT and this GPT kind. So you have your network that like GPT-4. What do they call them? Like these foundation models, and then you build like a ChatGPT with like some human in the loop reinforcement learning stuff to tweak it to to make ChatGPT, which actually uses this chat format. So I think it's kind of, it's totally a distinctive problem. But it's a totally distinct problem. But
but resembles,
kind of, like having like a foundation cloud rendering model, and then actually, I think it's like a really basic problem to have like a retrainable. And then let me just quickly go to there. So they actually say that they achieved a 24 times speed up. So it's actually not instant, but that's crazy. That's just crazy. Like 24 times speed up. So yeah, I believe that's quite cool. So it's not instant. So, but it's still, like, if it takes 12 hours to render, and then they showed here that using all interactions took 34 hours. I think then a 24 times speed up between the two.
That's quite good.
Yeah, absolutely. And and they also show here that, for example, this, let's look at this column, for example. So here they have the path traced reference.
Right. And their approach. I mean,
and
like,
then they have,
perceptually, you don't really see any difference at all. At least from my end, I don't perceptually, like, human observation point of view, I don't really see any difference.
Absolutely. And this is the Radiance predicting neural network.
Right.
And even zooming. And I think one really interesting point that I actually didn't see mentioned is that when you look at this is the path trace on the left, and this is the neural network on the right. And so they actually, it's more noisy when you use path tracing. So actually the neural network kind of smooths out these this kind of noisy. It's really interesting. So it has like a smoothing effect, and I actually didn't see this mentioned in the paper. But I think it's there. So if you look at it, I think it's like each.
You definitely have
it's definitely there. So, but I don't think this. I didn't see this discussed. But I think it's really interesting that the neural networks, they do naturally have a smoothing out effect.
Right. I guess that's also one of the effects with those Midjourney, those image generative AI techniques where they generate images. You see it compared with maybe with an actual real image. You kind of see the AI image is so clean. You just kind of get it. That must be an AI image, like, because it's so clean.
Right. So those ones work, like, as far as I know, like, usually in pixel space. But actually, you never see noisy images. So it's kind of like, I think noisiness is usually like an artifact of path tracing, usually, I believe, and like not sampling enough. But still, it's quite interesting. And this was 24 times faster to get your neural network prediction. So it's crazy. It's just crazy. It's really, really interesting. And I think just like I'm really interested to hop on over to your paper, but then just one more thing that I would like to briefly mention, and then because I realized that now it was kind of, we were wrapping up, but one thing we didn't discuss properly, we just hinted at it earlier, is actually the phase function that they use. So I mentioned that in my slides, I actually had their figure there. And they are discussing the constant isotropic phase function, Henyey-Greenstein approximation, and then a Lorentz-mean and chopped Lorentz-mean, where they cut off the diffraction peak here, so they make it scatter less in a forward manner. So they cut it off. And actually, it's really interesting because then they discuss that when they use this chopped Lorentz-mean, then they actually make the volume more sparse because that way they don't want to lose so much from the forward. So they actually modify the volume, because then they lose some of the radiance because they don't have it scatter in the forward direction that much. So they actually modify the volume to make up for this chopped off phase function. And then so here they say that they opt to use a full Lorentz-mean phase function for the first bounce, and then switch to the chopped version and its corresponding optically thinner volume. So this is saying the same thing more succinctly than I just said. And they also mention here that the chopped Lorentz mean estimation variance reduces estimation variance if they chop off the Lorentz mean phase function, and it also produces accurate results in front-lit or side-lit configurations. However, since the slight angular blurring due to the diffraction peak is replaced by continuing the perfectly forward direction, the very prominent effect of silver lining in backlit configuration is nearly completely lost. So this is also, I just read this because I think this is something I actually learned from reading this paper. This is completely unrelated to learning Radiance with neural networks. Is actually that, like, which one is that? Yeah, here. So here they compare using these different functions. So actually, this is silver lining. So silver lining is like, you know, the silver lining is that as the proverbial silver lining. Yeah, so this actually comes from mostly from single bounces. So when you have a sun behind your cloud and you're looking from here and you have a sun here, and then if the sun just bounces
just
one
tangents it, right?
Then that's why silver lining is there, I believe. So from their discussion, that's the impression I had. And then if they cut off the Lorentz mean phase function, then they lose this really prominent silver lining. So they still have some silver lining, but as they chopped off this exact forward scattering, then they lose this. So they chopped off this lobe part. So they actually lose most of this silver lining. And they also have the Lorentz mean here, where they have the silver lining properly. And then they say that the Hanyey-Greenstein approximation introduces a different
kind of biased or incorrect version of that, I think.
So it incorrectly increases contrast and produces a different silver lining effect than Lorentz mean scattering. And then they say they show here their kind of combined proposal, where they chop off the Lorentz mean, but only after the first bounce. So the first bounce, they just sample the Lorentz mean phase function, and then they switch on over to the chopped one. And so
I think it's probably was an interesting finding for the author's side, I guess. I would be quite skeptical that they were expecting that kind of effect. I guess that's one of the things that you kind of unexpectedly learn doing a research. Like because the main goal was actually to efficiently render clouds in a realistic way, but they also find something with the first bounce, you actually get this nice silver lining effect, and then you can combine two phase functions, and you get this good result. Let's say it that way. So it's really interesting, actually.
It's really interesting. Also, so thank you for everyone who wrote this paper. So Simon, Thomas, paper. Brian, Marcus, and Jan. It's been nice to read your paper. It's been fun.
We mentioned it the last time. Like, I'm seeing Thomas Müller's name almost every paper now.
Yes.
It's just crazy. Congratulations.
But also most of the other researchers who wrote this paper. Like I just see so many. I'm sure it helps if you are doing research at Disney and you're like really excited to do what you do. I guess it would be fun to meet them one of these days. So it's been fun to read this paper. So I think we pretty much touched on every part, I believe. So just to
thank
finish
you very
off,
much. Great. Oh, sorry, interrupted you.
Oh no! I just wanted to leave the slide on the
that's right. Okay.
Results.
Great. Really well done paper, I think, and I would definitely recommend to everyone who listens to give it a chance, because it's a well written paper, and with the figures with them, you get the overarching idea with a quick read, actually, I would say.
And also like why we started this whole thing with our paper reading circle is that we would like to increase the number of papers that we read as students. So I think it's really nice to get to read papers that you care about and that is really interesting to you. So So yeah, because it's
discuss it with your
not
colleagues.
straightforward to read papers. It's not
Right.
straightforward to read papers.
Yeah,
It's
it's
really
not
something you just
something.
pick up
Yeah,
by itself. If
exactly.
you have to put in the conscious effort. So yeah. So
Exactly.
also discussing
Yeah.
papers with you and the others is really like a really nice inspiration to actually read papers.
It's exactly that. That's one of the goals. Like, I mean, sure, podcast is nice to have it. Maybe we can influence other people to read more papers as well. But essentially, this is more of a egoistic maybe thing to do in a sense, because we want to read papers, and this is the motivation uh, part, so that we can motivate one another, and when we talk about papers, we also understand it better, I think, with other people, and it's basically fun, since like we are also quite enthusiastic about it as well. So yeah. So when you, for example, explain this paper, I'm more interested in real-time computer graphics than I actually am. It gives me extra motivation to an upcoming semester to understand better way about it, about real-time computer graphics, which I was like a couple of months ago wasn't really that. I'm not really sure about it.
Oh yeah, because you've been doing mostly offline stuff.
Offline rendering.
Yeah, right. Right. So I think I'm going to stop presenting.
And yeah,
sure.
Barney was showing me at the moment the original authors from his paper suddenly switch sides to NVIDIA. They have the paper.
Yeah. So also didn't discuss that. I believe it was a paper from 2017. So most people are not at this research during the time of this podcast who were doing their who were writing this paper there. So yeah, we stalked everyone down in the short break. We just read up on people.
Yeah, because like last time I mentioned like, oh, I'm seeing Thomas Miller's names almost every place, and you mentioned Jan Nowak's name, and suddenly we kind of realized, oh, there's this new paper where they're all from NVIDIA, and also Wenzel Jakob, who is one of the lead guy in realistic graphic labs in Lausanne, I think. So they wrote this new physics-based differentiable rendering paper about how to make this whole process more efficient, using actually with less samples, etc. Which we can maybe one day talk about, read about.
Yeah, absolutely. So especially with leading up to your paper about inverse rendering or differentiable rendering. Actually, is it the same? Like, is it the same nomenclature? So inverse rendering and differentiable rendering, are they interchangeable?
That's a good point. Not really. I would call I would call differentiable rendering a subset of inverse rendering. Inverse rendering is more of a generic term where you can say, okay, I have this thing, for example, input of reference images, and our goal is to inverse this rendering process so that I can get the initial parameters that I provide to the rendering algorithm, which produces this image, for example. With physics-based differentiable rendering, you actually specifically used differentiable rendering, and especially on what I did, they use a specific algorithm called radiative backpropagation, where they project gradients onto the scene and calculate the derivatives on the objects themselves, on the scene parameters themselves. So I would call like a subset of
Right. So there are like
rendering.
multiple ways to do it. So you don't necessarily have to get like a differentiable rendering process in order to be able to inverse the rendering process.
Exactly.
Yeah, because as far as I understand it, like it's also an inverse problem that you have. Like you would like to find which material parameters did this scene correspond to by looking at only the end result. So you would like to invert the process of feeding a material parameter and getting a scene, but now giving a scene and receiving a material parameter. Or it could be like a geometry, I guess, but you were focusing on material parameters. So that would be like 3D reconstruction, I think, just to toss around some random.
Yeah. No, that's
that's your right. Rendering, right? So if you would like to get like geometry.
Okay. I was actually planning to read this during the presentation, but let me actually,
Oh yes,
it
yeah.
would be a good starting point to this my paper. And this section that I'm gonna briefly read is from a course from SIGGRAPH 2020. Let me maybe first show my screen, my presentation, and where you can see the course name from SIGGRAPH. Where is the share screen and screen window or tab and PowerPoint slide. Okay, I guess you can see my presentation at the moment.
Yes, yes, absolutely. It's perfect.
Perfect. Okay, I will quickly jump to the first slide or the second slide. And the section that I'm briefly going to read comes from the SIGGRAPH course from 2020 from Zhao and his colleagues, but in this course there were
sorry to cut into just one more thing before we get deep into your wonderful research.
Sure.
Just to give some context. So this now we had like our first paper, and the way we plan to do these podcast or paper reading circle meetings is to have the second paper about the CESC paper, so student paper. So actually these slides that you're showing now, these are the same ones that you used to present your research at CESC in Slovakia in a beautiful castle in Smolenice. So just to give some context, right? So
yeah, that's the idea, and hopefully when you will also be presenting your work, I'm quite excited to also to again see your material, what you did, but also from other people. It would be interesting, and also I will have some questions about your paper and what you guys did, because I'm interested whether you guys planning to work on the same side of the research that you guys have done. So it would be interesting maybe to talk about that side of the as well. Yeah.
Yeah, I'm also looking forward to chatting about it. Yeah, but sorry again for cutting into your words. I just wanted to give
please cut me off, because I don't at the moment don't see your face, so I have no idea the facial expression that you're making. So please interrupt me whenever you want. Yeah. Yeah, I have no idea at the moment. Yeah.
You have no idea what I just did.
Right. Yeah. So, or let me actually begin with the presentation, and I will actually then jump to the mini text that I want to read, that we were talking about inverse rendering, and like this type of inverse rendering, one can actually say it might be or actually more of a task in computer vision field, which the text that I'm briefly going to read kind of talks about that. But before that, I think okay, I'm in the start of the presentation, if I'm not mistaken, and I hope you also see that. Perfect. Yes. Okay. So yeah, as Barney mentioned, this was the work that I did for CESC, Central European Seminar on Computer Graphics on Smolenice. It was a student conference, and the project that we're working on for that 4 or 5 months, and the focus was on translucent material parameter estimation in a physics-based rendering setting. So with that said, let me actually start. So here is the rough outline. First, I will show or introduce the essential ideas that we utilize in the project, then discuss the problem and goals, and then briefly introduce our approach and specifically talk about the optimization process that we implemented. And lastly, I will show some of our results. So with that, actually, yeah, before we start, let me quickly note that there is a fantastic course about differentiable rendering from Zhao and his colleagues from SIGGRAPH 2020, which provides really a great introduction to that field. And hopefully we can maybe in the future read as it's actually a course material, but we can also read it as a paper because it's structured that way. And we can maybe discuss it in one of the upcoming episodes. Yeah. So rendering is a relatively well-known problem. So imagine you are trying to render a scene. The procedure then requires inputs such as objects, light position, material information, etc. And we often describe all this inputs as a high-dimensional vector X that contains all that information. So then rendering is basically a function that maps this input into another vector Y, where Y is the generated image. So in inverse rendering, we talk about the opposite of this process, which we call it like inverse rendering. And our focus, however, is based on physics-based inverse rendering. So our goal is to invert this hypothetical function and obtain scene description from an image. However, please note that we can't really solve this problem directly. So the domain of physics-based inverse rendering is high dimensional, and which incorporates many different difficulties. So intuitively, one could maybe think that the task of inverse rendering is not a complicated problem. So for example, if you have an image of a red book, such as in this photograph, one would instinctively argue that the scene description should contain a book object with red-colored material. However, we should also remember that our goal is to describe reality in a physics-based manner. So the red book in the image is actually a combination of red pixels, and there could be several reasons why the image contains them. So in the simplest case, the red pixel might result from a red-colored Lambertian material. However, it might also be a result of indirect global illumination effects, such as the reflection of the red book on the computer. So in short, since the given scene description is high dimensional and complex, the generated image depends on that. And there's often not a direct way to find the inverse function to retrieve the parameters from an image or from a set of reference images. So which basically brings us to leads us to the task of inverse rendering as an optimization problem. So with this, we introduce an objective function, which we also talked about in the previous paper, that quantifies the current quality of the solution. So in the simplest form, the objective takes the L2 norm, the mean squared error of the difference image between the rendered and the reference image. And so we can do this and we can represent them that way because the images that we render and the target image are high dimensional vectors, so we can do this mathematically. So we basically take our rendering algorithm and plug it into this objective function, and subsequently we try the best set of scene parameter X that brings us closer to the provided target. Okay, so as mentioned previously, the domain we are in is quite high dimensional. So the problem then often is changed into a local optimization problem based on gradient descent. And that's basically the difference that we talked previously. Like inverse rendering would be really the generic name for the task. You can achieve or solve this task with different approaches, and physics-based differentiable rendering often chooses to solve this task using gradient-based optimization problem and differentiable rendering and combining these to find a solution. So basically at each iteration, we evaluate the objective function with our current state and differentiate the scene parameter with respect to this value. Mitsuba, which is the renderer we primarily use in our project, makes things a little bit easier by using the chain rule. I will not really go into detail, but the idea is differentiating the objective function first and then differentiate the rendering algorithm after and multiply them to get the gradients. So if we differentiate the objective function first, in the case of L2 norm, we get an image like this in the middle that you can see, which is simple to understand. It basically tells us the difference between where we are now and our target. And the second part is differentiating the rendering algorithm, which eventually gives us a matrix of derivatives from the rendering process algorithm. So consequently, we multiply these two to get the gradient that we need to apply into the scene and get closer to our goal. Obviously, the tricky thing is differentiating the rendering algorithm or differentiating the rendering algorithm efficiently and applying it into this process. but fortunately, Mitsubishi 3 handles this quite well using this radiative backpropagation algorithm introduced by Nimia David and his colleagues in 2020, and the extended version of that, which was introduced by Vicini and his colleagues in 2021. This is also one of those papers that we can also discuss in one of the upcoming episodes. They the way they do it really interesting, but hard to grab initially because it's a tricky little thing.
And by the way, I was just wondering about
Right.
one thing. So this works in pixel space, right? So you mentioned like it's a high dimensional problem.
Right.
So you literally have two matrices of RGB values, I guess.
Exactly.
And does it matter is it mentioned that whether it matters which color encoding you use? Because I guess you have like RGB and HSV and I don't know like which kind of space you are working in like
I think.
is it?
I think it doesn't matter. Obviously, you change the implementation depending on the format that you have. So, for example, on Mitsuba, there's also the spectral version. So you include so you can render the spec or to use the spectral rendering version, and they also have the differentiable rendering capability when you use the spectral rendering mode. Uh, Obviously, it's more difficult, also computationally, but it's possible. Yeah. So also another thing is Mitsuba also indirectly uses automatic differentiation. So it's also that's why also it's also possible to do that. But the render you obviously have to differentiate the rendering algorithm as well and do that efficiently. That's often the bottleneck. Yeah.
Yeah, it's very interesting. Yeah, I guess it's just a transform on the numerical values. So I guess
Right.
if you, but I was just wondering if it's because to me it's just so funny to literally just subtract one pixel value from the other pixel value and differentiate it.
Right.
It's just mind blowing.
Yeah, because I guess so like image space is one thing the way you can do that, but any differentiable objective function should work. I think that's also one of the recommendation in on one of the papers that I read. So if the objective function is differentiable, then you should be able to use that as a objective as a loss function. So yeah. Okay, so yeah. So differentiating the rendering algorithm, so we can, as mentioned, then discuss it in another uh, podcast or another episode. It's definitely really interesting. With that, actually, now let me switch to our project. So this was more or less actually related work in our paper. So up to this point is actually initial information to bring the audience to the room so that they can understand the ideas that we actually apply in our paper. Okay. So in our project, basically, the main goal was to estimate translucent materials from a given set of reference images. But we also provide a tool for inverse rendering and data management for that process. So we implement a gradient-based optimization algorithm that attempts to accomplish this task. We also provide a couple of workflows for data acquisition, for specifically image and scene file acquisition. So that's actually also one of the interesting things that maybe was quite, or maybe was a bit different from other papers in CHESC, that our paper was also included a lot of experimental part where we had to physically go to a location and take some samples or photograph of objects and kind of measure things in a controlled environment and then make sure that these parts work in a efficient way so that so that the experiment itself can be reproducible for other people. So that's kind of an interesting and really fun. It was really fun for me to take part in. So in this slide, you see also on the left one is the optimization result from synthetic data, and the right one is actually real-world alginate material reconstruction case, which I will then discuss in more detail. So, yeah, previously I mentioned this X term that contains the scene description information. However, in our project, we further specify X with following parameters for the task of translucent material estimation. So we propose to use two BSDF models. One is the surface-only Disney's principled BSDF introduced by Burley. And the second version is for volumetric rendering, actually, which combines Mitsuba's rough dielectric BSDF from Walter and his colleagues. That's also one of the paper that we have to read because it's such a well-written paper, like today's paper that you showed. It's such a well-written and interesting paper to read, and it's not really that complicated to grasp the idea. And it also contains a lot of experimental information, so that would be also interesting. Yeah. Yeah, so with rough dielectric BSDF from Walter and his colleagues, we also include a homogeneous participating medium interior. So the interior of the object that we have contains a homogeneous participating media. So as can be seen in this slide, so the main parameters of interest are the albedo, which represent obviously the color, surface roughness, specular transmission, index of refraction, and extinction coefficient. Okay, so let me be quick here. So this is basically for recap purposes. So here are material parameters that we would like to estimate. We define our task as an optimization problem using objective function G and successively repeat to get closer to our target. What I never mentioned is the term H, which basically provides additional constraints, such as minimum and maximum values for material parameters. So for example, RGB values then must be in the range of 0 to 1 per channel. Yeah, before I discuss the method, let me note two requirements that we had in our project. The first requirement is a set of reference images, which are shown on the left-hand side. And on top, you see some reference images for the synthetic test cases we had. And on the bottom, we have the alginate material specimens that we photographed actually from in the real world. The second requirement is then a valid Mitsuba scene file. So on the top right, you see some Mitsuba scenes in Blender. The top row again refers to the synthetic test cases. And the left one on the bottom is actually the virtual version of the material scanner that we use, where we've actually photographed the alginate samples. Yeah, and on the right, you can see the interior of the material scanner and the 3D model of the alginate specimen. So fortunately, Mitsuba provides a Blender add-on to export the Blender scenes for further use. Yeah, and yeah, with that, actually, let me continue with the approach. So yeah, we basically combine the differentiable renderer Mitsuba 3 with an Atom optimizer to estimate material parameter. In this slide, you can see the user interface of our tool. So basically, we first load a scene file, which includes the initial material parameters. We then also load a set of reference images, which can be used then in the objective function. Next, we select material parameters of interest, which then gets assigned to a newly initialized Atom optimizer by our tool. And optionally, we also select some optimization hyperparameters and then start the optimization loop actually. Yeah, let me continue with the optimization loop. So we basically initialize material parameter and then run the following loop for each sensor or for each reference image we have. So we perform first we perform a differentiable rendering step with respect to the selected material parameter, which provides which gives us a resulting image. Then we evaluate the objective function. Then we backpropagate the gradients using Mitsuba tree. Then we take Atom optimization step to find the updated parameters. We then ensure legal values for them by using box constraints. Then update the scene with these new parameters, and we repeat this process until either the loss tolerance or maximal iteration is reached. So this is basically the computational part of our approach, and in practice, we obtain relatively acceptable results. Yeah. maybe another time then I can also talk about the experimental part. However, the interest in, if anyone is interested, just check out the experimental part of our paper. I think it's one of the, I think the 4.1 section of the paper. Yeah. Okay, let me, before showing you the results, let me briefly mention the thing that I wanted to read. This is, the thing that I'm going to read comes from this course regarding Introduction to Physics-Based Differentiable Rendering. And the Wenzel Jakob, one of the authors of this course, was describing or giving a sense what they do in relation to computer vision. So he says inverse rendering is in some sense the central problem in computer vision. However, computer vision is quite different than computer graphics. In CV, there is some specific tasks to be solved, such as object detection, classification. Nowadays, these tasks involves machine learning, mostly use of neural networks. A lot of progress in network architecture has been made, consequently. So overall, in CV, the rendering algorithm in use have remained fairly simple, so mainly, mostly not physics-based. And there are also different attempts on replacing the rendering algorithm using like neural networks. Maybe NeRF could be one of them, in the sense that you try to reconstruct the scene. So in physics-based differentiable rendering, our focus is on computer graphics. So we focus on computer graphics and more realistic simulations. Therefore, physics-based inverse rendering, we have effects like global illumination, so interreflection between objects, complex materials, reflection, refraction, subsurface scattering, and participating media. And we most of the time, or we don't actually use neural networks. And he mentions that we actually shouldn't need them. So because we actually understand the underlying equations. So we can still use neural network inside or outside the renderer, however. So that's kind of interesting. And he continues briefly. So in computer vision, it is not that clear. So the underlying equations aren't that clear. So the tasks are actually unknown tasks. So he mentions, for example, object identification, task between dogs in an image or cats. That's you can't really basically you don't actually have an equation for that. Like there is not a direct equation that expresses the core of the problem. However, in
I mean,
physics-based
they kind of tried doing this, you know, like really earlier CV
right.
solutions kind of tried to do this, you know, like let's find an eye, let's find you know, and like let's combine these parts, but they kind of got super outdone by neural network approximations. But it's kind of interesting what you're saying. So I think it's really so as far as I understood this quote, so it's kind of saying that where you don't have underlying equations, it's really nice to use neural networks because they are great at like these, I don't know, like fuzzy matching problems, you could call these. Or, you know, when you have these, when you have to find what it means to have a dog and like what it means in terms of RGB colors to have a dog, because yeah, you can describe it in like words or something. But I mean, maybe that's also really not the easiest task, like describing what a dog is. But yeah, but other than that, you can't say what pixel. Yeah, but also, but I really like. I absolutely agree with this. So I think there is a nice idea there. But I also really like in recent research, and what I also really like to focus on is actually how you can combine the existing knowledge that you have by some equations that you have and know and trust, and then somehow give this existing knowledge to your neural networks. And I think this is really a thing that will advance computer graphics and numerical computations in general in coming years.
Right. As the paper you showed today, like this is exactly. I guess that would be a perfect example of what you mentioned.
Right? I say this is a really nice example, because you like kind of have like your ground truth equations, but then you like approximate one small component. But also what I really like is actually like differentiable simulations and differentiable rendering, where like, and I think differentiable rendering is also really nice because there I mean, you can intertwine the two because if you have like a differentiable subcomponent, but you can also take it like your grade. If for example you have a differentiable simulation, which I really like physics-based simulation, and then you can make it in a differentiable manner. Then you can intertwine the NN component and the physical simulation component, and like the gradients can flow through the neural networks, but also through your existing equations, because the paper that we just discussed actually doesn't do this. So actually, it sounds stupid to say this, like it sounds not stupid, but like it's not really precise, but the gradient don't necessarily flow through the existing, so you don't have gradients that encompass your current knowledge of the world and like how physics work. So it's kind of like its own thing. So it's kind of has, but what I really like about, and I will stop here because I think this is so what I really like is, for example, you know how the Navier-Stokes equations describe fluid flow, for example. So when you try to teach a neural network how to exert control forces on like fluid flow, then you don't want the neural network to learn how fluids flow. So you know that you just like to teach it how to control it and come up with a way to match some kind of function that I mean like some kind of loss function that says how well you control in terms of your given objective. So and in order to do this, you can have actually gradients of existing knowledge, so to say, or like of your equations. For example, like I think like physics-based deep learning and physics-based render, like, and also like differentiable rendering, but also differentiable physics I think is really a way towards encompassing existing knowledge, but also the spark of brilliance of neural networks. And just one. Also, have you read by any chance the Thinking Fast and Slow by Kahneman?
I think no.
I can really recommend it. I can really recommend it. I was it got recommended to me multiple times, and I think it also won a Nobel Prize, or I'm not sure if the author won a Nobel Prize, or his book is writing about his achievements that got him the Nobel Prize, I believe, but I don't want to mislead you. But I think it's really a well-recognized author and also book. And there he actually talks about these two kinds of ways humans think. Like, and we have like a system 1 and system 2 way of thinking, and one is like this spark thing when you just like see something and immediately know what it is, and just this it's the system 1 and fast, automatic, frequent, motion or stereotypic way of thinking. But we also have the system 2 way of thinking, which is kind of like the precise, slow, effortful, and it's really interesting because there is actually a nice podcast with Daniel Kahneman.
Is it this book?
It's
right.
This.
Okay.
Yeah. So actually, and he's actually really he's surprisingly knowledgeable about how this translates to neural networks and scientific and STEM related things, because he's actually, as far as I understood it, his focus is more on psychology and sociology, and not really like STEM, so not like hard numerical computation, so to say. As far as I understood it, but actually he has a surprising amount of insight how this all relates to neural networks. And there is like a really nice podcast episode of him, I think with Lex Friedman, if I'm not mistaken. I think it was part of the Lex Friedman podcast. And actually why I brought this up is because this system 1 and system 2 thinking actually relates really closely to what you were just referring to about CV and computer graphics, because actually you can think about having your ground truth or like your existing knowledge, like your existing equations, and solving them through Monte Carlo simulation, I don't know, ray tracing, or like like a discretization, like Laplacian, like Eulerian or Lagrangian discretization. So like Eulerian would be like grid based, or Lagrangian would be like a particle based discretization methods for simulations. And then you kind of iterate them over time and evolve them over time. So it takes a lot of computation to do this. But then you have your neural networks, and actually neural networks are this kind of fast automatic thing. So once you train them, they actually give you like just an answer like this. And so they are actually, this is called at inference time, so when you already train them. And it's actually really interesting to think about them. So kind of to fuse the two. So when you kind of add this neural network component into your existing mathematical or physical formulations, then you get the best of both worlds, because it actually knows how fluids flow, or how photons fly in clouds, or something like that, or what your model is for describing how photons fly and fluids flow. But then you also get this intuitive spark of brilliance kind of system one thinking, or at least that's the way I understand it right now.
Interesting. Yeah, it's definitely a really interesting subject to speak about. I'm definitely going to check out that book. And I lately I also saw some tweets actually from Wenzel Jakob, the quotes that I made, and he's also kind of sometimes mentioning about this stuff and how many of the papers right now have become a lot of about using neural networks, and how actually we can maybe utilize already known knowledge and incorporate it with neural nets, etc. So yeah, it's really interesting, and from a student perspective, it's kind of a bit pity that we, at least in University of Vienna, we didn't really had a lot of chance where we had to learn about whole this side of the computer science. So I hope we will be seeing more or learning more about it in the masters. So let's see.
So you mean more about the philosophical side, or more about combining neural networks and knowledge?
Combine. Yeah, maybe also the philosophical side would be also interesting, by the way. But I actually meant more the implementation side, or the using of neural networks in general. Yeah. But the philosophical side feels interesting.
Right. Yeah, I get what you mean, but also on the other hand, I think it's quite experimental currently. So it's actually kind of like current research. So like especially on a bachelor level. So when I did like an exchange year at the TU of Munich, so at the Technical University of Munich, actually most courses that really fascinated me revolved around this notion of fusing differentiable simulations and neural networks.
They were mandatory courses? Or?
Oh no, I just cherry picked. I just cherry picked the courses that I was interested in. So they were mostly graduate level courses, I believe, that tackle these kinds of differentiable physics and neural networks kind of concepts. So I think it's really interesting, because you have to come at it from two sides. Like you have like deep learning sides, and to formulate like like matrix factor multiplications that like ReLU at the bias, then ReLU, and to kind of like get, and like you have to separate, like you have your validation training and test sets, and then like kind of this kind of how to do this well. But then you also have like the physical simulation kind of subject, and they are totally unrelated in a sense. Like when you learn it, like how do you simulate fluid flow? How do you render? How do you do ray tracing? I don't know. Like it's kind of
your paper was about fluids, right? Like in that context, how they. So it's going to be interesting when you also talk about.
It's kind of like a prelude to that, to be honest. Like I usually try to control fluid flow with neural networks by training the neural networks via differentiable physics. So it's literally like you don't want it to learn how fluids flow, you just want it to learn how to control it. So it's really funky. I think it's really interesting and exciting, and especially this adding existing knowledge to neural networks. Because I think just one more thing before we go, because I really miss talking about your paper.
No worries. we talked about it so often, so I think I just kind of bored of that, to be honest.
But it touches a really interesting thing, like so many random really funky things. But yeah, what I wanted to say is that I think one core notion that this concept touches on is that you would actually like your neural networks to be dependable, because like from the one side, it's really computationally expensive to actually simulate or render your equations. And then you can add the neural networks. Oh my God, it's so good because then it's so fast and it's a system one kind of fast brilliance spark insight. But then on the other hand, you have your neural networks which have this system one kind of thinking that gives you like really fast, automatic, frequent emotion, like what's written here on Wikipedia kind of thinking. But on the other hand, it's not restricted to actually give you good answers. So you would actually want to have existing knowledge that describes how the world works. So you would actually like to restrict your neural networks, or rather use this existing knowledge because so you would like your neural networks to be dependable. So actually, if you just add everything, like all of your states about fluid flow, and you would like it to learn how fluids flow, it could just give you an answer that doesn't describe well how fluids flow. So it could actually learn a worse representation of fluid flow than what the Navier-Stokes equations would give you, or it would learn or any other problem. Like this is just something on the top of my mind, on top of my head. But I don't like it could learn actually a worse representation than what you actually have. So it's actually really nice to actually use this knowledge to make neural networks dependable, because this is something that comes up really often in current discussions about AI or neural networks, like how can we trust AI, or especially like even without mentioning anything societal with bias on a society, but even like looking at it from an engineering perspective, like some fault tolerant system, or some I don't know, a control system of an airplane, or I don't know, a train, or something that costs human lives if you don't do it well, or something that you use to calculate suspension of a bridge while you construct the bridge. So
interesting. Really cool stuff. I mean, really interesting stuff, and we will continue to talk about this, I think, in the upcoming episodes as well, because like it's maybe we want to talk about, maybe some people are not really interested in that side of it, but nevertheless, I think the academia kind of converges in that direction anyway, so we will most likely talk about it in more detail.
I think there are great papers currently getting published on the topics, and they are really current papers, because actually the paper that, like, I think it was from 2017, like the deep scattering paper that we just went over. So actually that's like what, 6 years? That's like an eternity with current advancements in AI. So it's like a lot of time. But on the other hand, like the NeRF paper is what, like 2020 or something, or it's like
2020,
3 years. Like
it's
like.
It's
just
crazy.
wow, it's like years or so, and it already has like I don't know how many citations, like thousands and thousands.
And it's like we talked about it last time as well, how the actual NeRF implementation become kind of not redundant, but kind of outdated in a sense, because how many have been published in the NeRF section, and how
right. So I think they use some they use planoxels to like actually don't use neural networks to do the same thing. So that's also kind of the same discussion that we just had about using or not using neural networks. But I think in a sense, actually NeRFs can be thought about actually using existing knowledge, because they actually, the way they teach their neural networks is using actually volumetric rendering. So you actually have an existing knowledge that you use to describe your scene, and the way you actually take the derivative of how well your network did, like that actually uses volumetric rendering, and they formulated that in a differentiable way. So that's actually differentiable rendering in a nutshell.
Actually, that's true.
For you, so it's that's also, I believe, is a prime example of using existing knowledge, or like but I think coming up with new things with regard to teaching neural networks, I think you either come at it from a mathematical perspective, and you do some crazy mathematics to derive some better sampling, better mathematical formulation for neural networks, or you come at it from like a model. Like you incorporate some existing knowledge, or you can also come at it from the engineer perspective to make like learning more feasible, and like handle the 80 terabytes of scene data or something. But I think think like a pillar stone of current advancements in AI and deep learning is actually how to incorporate existing knowledge, or at least that's my current perspective on it. I think it's really, really exciting.
Really exciting, yeah. I definitely agree. Like, it changes so quickly, so yeah.
Yeah, it's true. That's true. That's true. That's why it's great that we are doing these paper reading sessions to
Yeah,
getting people
exactly.
to read more and more papers, because you have to read it like newspaper.
Exactly. Keep up to date. Like, yeah. Okay. Let me finish the presentation with the results, and then we are actually finished with the podcast, at least for the first episode. Trying to find my presentation. Okay, I think this is the slide. Okay. I think you can also see the slide right now. I hope.
Yes, I can.
Perfect. Okay, then let me continue lastly with the results. So, yeah, as I mentioned previously, we propose to use two BSDF models. In this slide, I show some results from the synthetic test cases we have using principled BSDF. So the idea is, from initial dark gas, we optimize color, roughness, spectral transmission, and index of refraction. And as you can see, we obtain acceptable results in 100 iterations. So we get quite close to the provided reference images. In the next slide, I'm showing some another synthetic test case, however, this time using rough dielectric BSDF and homogeneous media, homogeneous participating media interior. So as previously, from initial dark gas, we optimize color, roughness, however, this time extinction coefficient and index of refraction. Again, we get quite close to the provided reference images in 100 iterations. The last iteration and the middle column that you see, then you can see the noise. That's because of the low sample count. However, if you increase the sample count, you get almost the same as in reference images.
Right. And just one question, like here, everything is a scalar value, right? So these 4 parameters on the left, these are all scalars, so nothing.
Not actually.
Or are these textures,
right.
or is the extinction coefficient just one scalar value, or is it dependent on the position?
That is actually, extinction coefficient is a scalar value, index of refraction, and roughness. However, in this case, albedo is represented as a grid volume, so it's actually a texture in that sense. Yeah.
Oh, okay.
And also on the previous example, okay, this is not the, this is the, oops. In the previous example, the albedo is also is actually a bitmap texture. Yeah, and however, other parameters like roughness, spectral transmission, and index refraction are actually scalar values. So that's one of the also tricky thing to do. However, we kind of managed to do this using grid volume to give a varying color to the object. So we had to use texture or grid volume, or three-dimensional grid volume to represent the color in a varying way. Yeah. However, important thing to note here, the participating medium that we use is homogeneous. That's why it's actually working well. And the extinction coefficient in that case is a scalar value. Yeah. So yeah, with the synthetic test cases, our goal was to see whether our approach worked. And in our paper, we also have an ablation study where we discuss what works well, what doesn't work well. So if you're interested, you should definitely check out. But basically our main goal was actually to estimate translucent material parameters or properties from real world data, which brings me to the next slide. So we see in the slide results from alginate specimens. This is a material from this is a new type of material from material research, actually, which provided to us from Technical University of Graz It's kind of a weird material. It's kind of translucent and kind of has a soft feeling to it. And the idea was to reconstruct it so either the architects or the archaeologists can use them in their software, where they can place this type of material into their software and see how objects would look with alginate material. Yeah. And yeah, in both rows we show using the optimization using principled BSDF. And one thing to note, however, that we actually divided the optimization process into two parts. In the first section, in the first part, this is the first part where we optimize the material parameters using a constant RGB value. However, in the next slide, does the second step of the optimization. We actually restarted the optimization by using the optimized material parameters from the first part and changing the representation of the scalar value, thus the color, into a bitmap texture. So in both cases, we get relatively acceptable results. However, beware that the bitmap textures also contains a lot of information here. So which might not 100% accurate. So for example, the shining parts that you can see above is actually contained in the bitmap texture and doesn't really originate from the other material parameters, such as roughness parameter or index of refraction. So that means that we have to still improve with our approach, and we believe.
Yeah, but also like from a single view, this is not even possible to predict. Like you can you can never know whether it's like, until you have multiple views, you can never know whether it's specular or just albedo.
Exactly.
Yeah.
Yeah, that's actually one of the future work now. I think I mentioned it at the beginning. We have now we have some ground truth values for some samples, and we're gonna do a new test cases where we will have multiple views for the object, where we can try our approach in a more constrained environment, where we can test whether it is working or not. So as you mentioned, multiple view is necessary for especially for translucent materials. Yeah.
This is so cool that you get so close to the reference. This is crazy. This is absolutely marvelous. And one thing I'm still wrapping my head around. So you took a picture of it, as you showed it before, and then you also had to 3D model it, right? So you had to like you had to polygonize it, so to say. So you actually made a 3D model of this globe or this object.
Right.
And then you kind of masked out. So this is the lower right, right?
Right. You see the Mitsuba scenes in Binder slide, right?
Yeah.
Right. Yeah. That's the model of the alginate specimen, right? Exactly.
Oh, so this is flat. So it's flat?
It's kind of a flat, but it has still a thickness to it, the alginate material. So it's a rough approximation of the model. Yeah.
Oh, I thought it's like, there are those globes that have like a dent in them that they use for highlighting different materials. You know that they usually showcase different materials with it, like for, I don't know. I totally thought that they are globes. I didn't know that it's just flat.
Yeah, in this case, so the alginate materials were quite flat. I don't know, from thickness side, like, I don't know, 5 millimeters or something like that, maybe. So
I thought that these are spheres.
Yeah. Yeah.
I literally thought when you showed it that you just put the sphere on top of it. Like usually, yeah. I don't know why. Like, yeah.
No, it was actually kind of a not cylinder, but like a one-dimensional cylinder, I guess, if you call it that way, like a circle with a thickness to it, and yeah, it looked like this from the side. Yeah, but as you mentioned, we had to approximate it in Blender so that we could actually reconstruct the materials from the images. Yeah.
Okay. I totally thought that it's like a globe. I don't know why, but yeah, but you should show. You told me that this is the model that's used, but I totally thought that that's just the base object and you put like a globe on top of it or something. Yeah, I don't know why I thought that.
But yeah, maybe from the angle of the photograph, especially the bottom right part of the material, like it kind of is curvy.
Yeah, it kind
That's
of
also
looks curvy, yeah,
nice.
and especially with this
Yeah,
dent in the middle. So I totally thought that
right.
it's like, you know, like
Yeah.
globe and with the dent in it. Yeah, they sometimes use for showing off materials.
By the way, the dent you're mentioning, like this is a really, let's say, highly important material in the lab. Let's call it that way. And it's called the toilet paper. Like I had to actually find something to hold these thin materials so that the translucency was depictable. So I kind of found eventually at the end, like got the toilet paper roll, get it out, all the toilet papers, and placed it on the bottom of the material so that we captured the translucency of the object. So
The things you have to do for research.
yeah, exactly. It was really
Ah,
fun.
that's
Yeah.
so cool. Oh, so the dent is literally a toilet paper roll
Yeah,
sticking
exactly.
out. Oh my
Yeah,
God. Okay. Okay. So it's not that thick. So it like oh
yeah,
wow.
yeah. I think on the
Wow.
top, on the glue material, you see it much better, like the curve of the
Yeah,
toilet
yeah. Now
paper.
that you say it, yeah, it literally looks like a roll, like a paper roll. Oh
Right.
my God, that explains so much. You should have led with this during your presentation. Oh my
Yeah.
God, oh my God, this is so funny. This is so fun. You can never listen too much, too many times to a
Yeah.
presentation. I believe, like there
But
is no such
it,
thing as listening to something too many
yeah,
times.
but
Wow.
it's
Okay.
like it was like last minute solution because I remember it was like 6, 7 months ago, I think now. And I went to the university, which technical university, but the architectural department where they had these materials. And like Professor Fershin told me, oh, you can photograph using this material box, and here are the materials, and you just then continue with his work. And I was kind of thinking, okay, this is cool, but how can I actually see the translucency, or how can I actually capture the translucency of the object? And I didn't really have anything with me, and then find toilet paper and just put it up on the toilet.
Yeah. Right.
Mm, mm. Okay, yeah, that's more or less the presentation. So yeah, that's actually from my side. Okay, I think stops sharing.
Cool.
Great. We
Cool.
are finished with I think with the first episode.
Yeah,
Um,
and I would
do
say
you want to
yeah.
say any?
Yeah,
Do
I
you,
think we also touched
yeah.
on like, like the marginal areas that we could like discuss. I think we did like a
Right.
random like system on system thinking,
Right.
let's differentiate and plug it into neural networks and vice versa. So plug neural
Yeah.
networks into stuff that you can or cannot differentiate. So yeah, yeah. I think we also did the we did
Yeah.
that a
It was.
bit too early maybe. So maybe this would have been the
Yes.
place to talk about it. But
Mm,
yeah, it's been so nice to go through it
mm.
with you again.
Yeah, it was really fun. It was really fun.
I hope we get to do this
Yeah.
another time.
Yeah. I hope you present next time your paper.
Yeah, we'll see about
For
that
yeah,
because
it would be
yeah,
good.
yeah, we will talk about it. I would also really like to listen to talk with Mate about his cloud rendering
Right.
paper
That's
because
true. Yeah.
that would also be a really nice follow up to have some volumetric thing
Right.
because he had
That's
like
true.
I totally blew my mind and it totally
Mm,
blew my mind when he presented
mm.
his real time cloud rendering. Like
Yeah.
I loved that so much. Like it was
Mm.
really nice.
Yeah.
But
His
yeah,
presentation was
talking about my paper
perfect.
sounds
Yeah.
great. Yeah.
Mhm.
And also we hope to get more people on board for next time and to get more
Yeah.
people on the
I
call.
think it looks more optimistic for the next time, like at least from the
Yeah.
reactions that we got from the group chat.
Yes.
Let's see.
Yes. Yes. Yeah. So what do people say at the end of a podcast session? Like subscribe and
Yeah,
stay tuned.
stay tuned. Yeah, wait for our episodes, I guess, because we plan to do the next session in 2 weeks. So
Yes.
yeah, and
Yeah.
well, we still have to think about where we can publish this podcast.
Yeah,
but
and
we
actually we are
also,
still undecided whether we would like to publish this anywhere or not, or where. So, but if you are listening to this somewhere, and by you I don't mean John, then then we probably ended up putting it somewhere. So yeah, if you have any feedback on how it would make the most sense to do these episodes and what you liked and what you didn't like, then yeah, just shoot us an email, comment, anything. So
and
yeah,
if
we
you have
are.
also maybe paper suggestions, maybe in
Yeah,
the future we can also accept some paper, accept in the sense like,
absolutely,
yeah, we can
absolutely.
also read some papers that if we have some viewers that they find it interesting, that would be also a possibility. Yeah.
Yeah. Yeah.
Okay, let me now stop the recording. Bye, everyone.
Bye, everyone.
Okay, record, stop recording, stop.